Hey there, fellow members of the concrete construction industry. Before we get started today, I want to take a moment to address something important. As professionals in this industry, we understand the challenges we face and the constant need for up-to-date knowledge and valuable insights. That's why we're here, providing you with a podcast that caters specifically to our community. But let's be real. Producing the show requires a significant investment of time, effort, and resources, and that's where we need your support. We're embracing the value for value model, which means we're reaching out to you, our dedicated listeners, to help us sustain and enhance the podcast. Think about the value you gain from our episodes, the practical tips, the industry trends, and the expert interviews. We want to keep delivering that value to you, but we can't do it alone. Instead of interrupting your listening experience with ads or sponsorships, we're relying on your generosity. If you find value in what we do, we kindly ask you to contribute what you can. Your support helps us continue producing high-quality episodes that address the specific challenges and interests of our concrete construction community, from supporting the cost of equipment and hosting fees to bringing in industry experts for exclusive interviews. Your contribution makes it all possible. We understand that every business and individual has different capacities to give, and no amount is too small. Whether it's a one-time donation or a recurring contribution, we appreciate your commitment. By supporting us, you become an essential part of our mission to provide valuable content tailored to our industry's needs. Together, we can elevate our professional knowledge and expertise. So please take a moment to visit our website, concretelogicpodcast.com, where you'll find a donation page that makes supporting us quick and easy. Thank you for being an integral part of our concrete construction community. With your support, we'll continue to build a brighter future for our industry. What is the most used man-made material on Earth? You guessed right. It's concrete. Look around. It's everywhere. Sidewalks, driveways, foundations, floors you stand on, and even entire buildings are made out of concrete. So why don't we discuss it more? In each episode of Concrete Logic, we will explore one concrete-related topic with the help from industry professionals that are shaping the future of the trade. We'll talk with suppliers, contractors, architects, engineers, specialists, and even some proponents of competing materials about their views of concrete and their vision of its future. And welcome to another episode of the Concrete Logic Podcast. And today I have another returning guest, Dr. Jon Belkowitz of Intelligent Concrete.
Pleased to meet you.
Yes, sir. Good to have you back. He's a concrete guru consultant. He's a holder of patents, as we've discussed in a prior episode. One of my favorites, by the way. I did ask you, I asked the LinkedIn community what was their favorite Concrete Logic podcast episode, and I modestly picked somebody else's episode, which I appreciate, but I always enjoy talking to you, Jon. So thank you for coming back to the show today.
Heck yeah, it's a great show.
So today we're going to talk about colloidal silica. I know just enough to ask some dumb questions about it, but Jon has some patents on it and studies it a lot, is my understanding. Is that a correct statement?
For Father's Day, I just got some new books, like awesome books on colloidal silica. So best Father's Day present of the year, and I've already cracked into them. So I do love this stuff, and I've been working on it for a very, very long time. And it's a solution to a lot of the problems that we have in the concrete construction industry.
Yeah, I think the first place to start, Jon, is to explain what the colloidal silica is. It's a colloid, right? Is that the right way to say it?
So we could break down the etymology of the term colloidal or a colloid. It sounds so Russian when you say colloid. So I really do love saying the word, but it means a suspension of something that normally would be impacted by gravitational forces. Now, there's a range of those particles. It's normally less than 1 micrometer. And if you don't know what a micrometer is, that's 10 to the minus 6 10 to the minus 6 meters, all the way down to about 1 or 2 nanometers, which is 10 to the minus 9th meters. So do you know what that means, first of all, that scale?
No, man.
So when I say 10 to the minus 6, instead of being 1 meter, it's 0.006 zeros and then the 1. That's how small it is, right? When you do a nanometer, it's 1,000 times smaller than that. So instead of 6 zeros, it's 9 zeros. And then it's the 1. So when you look at a hair on a human head, it's around 100, not on your head or my head, but it's around 100,000 to 150,000 nanometers in diameter, right? When we look at Class F fly ash, just like in this picture that I'm not showing right now, is around 1 to 100 micrometers in diameter. So this is a slide that I often use that when we're trying to compare what is nanosilica in this colloidal suspension versus what is something that we're used to using. So we're used to using Class F fly ash. We know it has a silica content for pozzolanic reaction. We know it has a ball bearing effect. It was once used as the poor man's water reducer, all this jazz, and it's very, very small. So when we look at it under the microscope, this one in particular on the left, this shows Class F fly ash. Now, granted, this was from the 80s. Doesn't look like this anymore, but this was the ball bearing pozzolanic inducing material that we used in concrete. And to the right of it is this nanosilica sized particle in a colloidal dispersion, right? So a colloidal suspension, we call it colloidal silica. Milk is a colloidal suspension of fats and proteins. So it's got to be a universal suspension that either happens naturally or we manufacture it that way to keep something in suspension that normally would not stay in suspension. Now, that can be anything, but for our intent and purposes, it's nanosilica-sized particles. Does that make sense?
Yeah, I think so. Could you say it's like oil and water or no?
Could you say it's like oil in water?
To get an idea of how colloidal silica, we're talking about it's in suspension in concrete, right?
It's really hard if you've never made Italian dressing, really freaking hard to keep the oil and the water mixed. Normally, you have to put something in there to break the oil down, like an acid, like a vinegar or lemon juice. So when you don't do that, the oil pulls to the surface, right? And you have the water below it. What silica will do, if it's not suspended, if it's not a colloidal form, it'll cake up, it'll agglomerate together, it'll cake up, and then it'll fall out of solution and stick to the bottom.
Okay.
So where oil will go to the top, silica will go to the bottom. So colloidal means that you're not going to have that caking problem on the bottom. It's going to be beautifully suspended in water. And BTW, which is what the kids are saying nowadays,
by the way,
BTW, save some time. It's a liquid dispersion, right? When we're talking colloidal silica, it's that liquid dispersion of nanosilica-sized particles. It's clear to milky, and the larger the particle, the more milky it is. It can have a surface area between 80, it's really 2,700 meters square per gram. This is specific surface area, and your particle size can range from about 2% solids up to 50, but more often than not, it's 15 to 50% solids.
Okay. So where does it come from?
There's different ways of making nanosilica suspensions. I think the most, the friendliest way I can say it with all the different patents out there is you can either grind sand up really fine and then suspend that really fine sand in some type of suspension or some type of medium. Normally it's water or at least a liquid. And then the other way of doing it is growing the particle. So the other way is getting some type of a monomer that has, or some type of a basic solution that incorporates a silicate. And, normally we have potassium silicate, a sodium silicate that we put in solution with an acid. We rip and strip off the salt, and what happens is the silica just starts stacking up on each other and growing into these different shapes. The bigger it gets, the shape changes. So here what we have is this nanosilica particle in solution. It grew. If you took a string of spaghetti and wrapped it on itself, that's what the nanosilica would look like. And that's what this is. It's a spherical nanosilica. It's around 20 nanometers in diameter. So it's a nanosilica ball, but it's got a bunch of silicone dioxides, SiO3, SiO2 sticking outside of it and inside of it.
Gotcha. So it's manufactured.
There are some natural methods, but they also include a lot of impurities. It's like getting a Cab Sauv, and if you like wines, if you get a Cab Sauv, oftentimes it's not 100% Cab Sauv, it's 85%, and then there's a bunch of other stuff in there. So when you manufacture it, which has a pretty significant carbon footprint, which is a necessary evil, especially with how much cement we can reduce from this stuff and how much durability we can enhance and increase in service life. But when we talk about the naturally occurring ones, they normally come from geothermal juices or other mineral springs where we have a heating process. You have a bunch of minerals, you have a bunch of salts, and they cool and form together, and voila, you have this nanosilica solids in solution. But normally it's with a lot of impurities.
And so I believe listening to you before talk about the subject and on your YouTube, again, I'd recommend folks check out Jon's YouTube channel, Intelligent Concrete. Lots of good stuff there. But I think in a prior presentation, I saw you mention it was at the early 2000s when colloidal silica was first used in concrete. Is that correct?
It was late 90s where it was first used. I think the major contribution, and he'll argue with me every freaking time about this, the major contribution was Brian Greene's work from the U.S. Army Corps of Engineers, and it was using ultrafine amorphous colloidal silica in a rock matching grout. So it had nothing to do with concrete. The significant use of nanosilica in concrete, I attribute that to Joe Shetterly and Specification Products. And to me, he is the real champion to getting this technology out to the masses, getting it out to the ready-mix industry. And man, he does it unapologetically. So yeah, those are the forefathers or the champions, or forefather and champion of nanosilica for the concrete construction industry. And with Brian, if you read his paper, he wasn't using it to enhance concrete. He was using it as a viscosity modifying agent. Turns out it increased the density to the point that it wasn't just water permeability, it was wave attenuation of nuclear payload or blast loads that were changed to, as the title insinuates, the rock matching grout, as opposed to the xanthan gums or dextroses or celluloses that we had used in the past. And of course, with that, there was a strength development too, but that's something we can get into here in a little bit. And then with Joe, for pavements, overlays, bridge work, it's amazing what they're doing at Spec Pro. Absolutely freaking amazing.
Yeah, he was on, I forgot which episode number it was, but yeah, we had Joe on here, and we We talked about the product a little bit and his background and how he discovered it, and he actually used it on his own projects. Signed his life away to warranty his work and all this other stuff.
And he didn't have to. He had a freaking golden parachute. He was good to retire and a very comfortable lifestyle. And he's like, you know what? Nah, I'm going to jump into the fire with the frying pan.
Yeah.
You did a great job on that interview and talking to him. And I think we're going to have him on the Colloidal Silica and Concrete Association. But anyway, come on, let's get into your questions, man.
Okay, cool. Yeah. So I was sharing with you. So I'm colloidal silica's, to my knowledge, is not used very much in my area in the Mid-Atlantic region. I don't hear people talking about it, and I think it's just because folks don't know what it is or how it can benefit them. So we're struggling out there with new cements,
right?
Lack of availability of some SCM, slag and fly ash and things like that. And we are, as a industry, and we beat this over and over again on the podcast, we're so reluctant to try new things. But this is the one that's one thing, the colloidal silica has really caught my attention, and I've really would like to see it utilized more and become, if it truly is what it is, and I think it is, because I keep studying it and I keep asking folks like you and Joe questions about it. It just sounds really useful, to say the least. As we would call it an admixture. Is that a correct statement, John?
I think for now that's one way of saying it. There's also a topical admixture too, or topical additive form of this. So, yeah. But I think admixture in new concrete is fantastic. And specifically, we use ASTMC type or ASTMC 494 type S, which is chemical admixtures for concrete specification, standard specification, and that type S is for special performance. So I think that is put. We are creating a new ASTM for that WK. It's either my zip code 80106, which is either my zip code, or it's 80963. I always get it mixed up with my zip codes, but I'm on that committee or subcommittee, and we're creating a new STM for colloidal silica that matches more like the fly ash standard specification, more palatable, less barriers to entry, and more directed towards the manufacturer and the end user. So, and that falls under the SCMs. So there is a new ASTM coming out for that, for colloidal silica for concrete.
Okay, so it'll be considered an SCM versus an admixture. And okay, gotcha. All right. I was sharing with you that I came across something recently in a specification about ASR, which stands for alkali silica reaction, which is terrible for concrete. I guess the folks describe ASR as the cancer of concrete, right?
So I've got a rudimentary drawing here that goes over the alkali silica reaction formation. So ASR gel formation. And what we have is many things that we can't get past. Let's just break it down to two things. We have a cementitious matrix, that gray stuff that has alkalis, that has other types of salts in it, and moisture and pores. Okay. Then we have our aggregate, which in certain areas can be a tetrahedral or reactive form with these salts. Over time, this silica and these alkalis plus moisture combine at you see here, this center picture shows the rock in the middle of the paste, the gray stuff, it creates this gel. And this gel, while it's very elastic, it grows at this interfacial zone between the paste and the rock where there tends to be a lot of pores, and it starts expanding and opening in open space, in free space, creating these internal pressures. Well, these internal pressures overcome the tensile and shear capacity of not just the cement paste, but oftentimes the rock. And it ends up cracking the concrete from within because of these internal pressures. Now, once that cracking starts, then you have this influx in this third picture of water and more salts, and then it's just a vicious effing cycle where mature ring, immature ring of gel and more gel starts cracking. And this, scary enough, this can happen within 20 years. It can also happen within 24 hours. I show this picture, which is a book. I wrote a book on ASR. It's called The ABCs of ASR. And it's a fantastic dictionary on all the things you have to worry about ASR. I don't recommend buying the hardcover or the soft cover. Get the electronic version. It's $15. And the hardcover, which is a small guy like this, is like $135. And as much of an awesome book it is, I'm not getting the profit. It's all going to Blurb and Amazon. Get the ebook, and it'll show you pictures like this where they are, but this is ASR damage on a live structure in the United States. And what you see here is the after effects. Nobody cares about ASR until you start getting issues like this where you see this gel like stalactites, or is that mites? Anyway, stuff dripping out of the concrete, and that brown stuff is the steel corrosion that, is caused by the failure inundated by the ASR. So you have this combination of failures. It's rarely ever the ASR gel that causes primary failure. It's normally a something that pushes the snowball down the hill, right? It starts the failure mechanism. It's not the straw that breaks the camel's back. It's normally the steel failure. Now, that being said, I would call ASR more like the herpes of concrete.
Oh.
Yeah, it's a little bit grosser. It looks like herpes too, or it looks like a cold sore. It's oozy, it's gross. You normally see it at the surface, and it shows up in different forms. But when we look at it under the microscope, here, it is in Denver, Colorado, right? Where it's been exacerbated by the de-icing salts and brines and the wetting and drying cycles. But when ASR damage, when it has a very significant look to it. And primarily it's these Isle of Man cracks that are 120 degrees apart. They look like the flag from the Isle of Man. That's why we call them Isle of Man cracks. And they have these salts and gels coming out of them. But when we put it under the microscope, it really is one of the most beautiful things in the world. This is an ASR gel rosette, and this is under a scanning electron microscope. And I'm going to zoom into it because as nasty as it is, the beauty of this is where the destructive nature lies. Like it's something from a zombie apocalypse movie.
Looks like a wart.
As we get closer into it, it goes from this bubbly rosette that you can start seeing this fibril, wispy-like morphology. And it's those needle-like fibers that create this environment that imbibes or draws more water in, right? These small pores create a capillary suction that draws in water and salt that creates this vicious cycle of more gel growing, right? And to stop this ASR gel mechanism from thriving and surviving, what we need to do is not only have a chemical manipulation, but we also need to have a mechanical impact on it as well. And that was part of all my research is how is the impact of nanosilica size and surface area mitigating the ASR gel polymerization process, and to understand that you have to fall in love with the herpes of concrete.
Oh. But is ASR the result of, I guess, lack of better words, is the aggregate, the dirty aggregate, and the type of cement? It's a chemical reaction between what we're using now as those two materials go. Is that the root cause of it?
So there was, and I'm so surprised I don't have this paper in here, but there was a wonderful paper written by Katie Bardaget, Doug Hercom, Kurt Von Fay from the Bureau of Reclamation. And this was back in 2009. And they cited, and I'm doing this from memory, so you'll have to forgive me. They cited 3 reasons that ASR was going to become more of a concern in the future. And what's really nice about this paper, like all the conclusions are right up front, so you don't have to skip 130 pages to find them. God bless them. So the first thing is, back in the late 90s, we here in the United States had a huge cement production shortage, and we were bringing in a lot of cements from Asia. And these Asian-based cements had higher alkali content, were finer. We were getting 28 days strengths in 24 hours. Now, when we went back to the more Hoover Dam cements that we were used to before this cement shortage, the contractors pushed back and said, hey, we want these Asian-based cements, or these higher reactive cements. Well, the problem with those higher rate of reaction, you'll get something for nothing. You also have a higher alkalinity. So there are cements that we had as high as a 1.76 on sodium equivalent content, and that goes into our ASR engine. That gel polymerization alkalis is what fuels that engine. Now, we were also going through this change of using quality fly ash to just using fly ash. There was a huge P2P movement in the early 2000s. I don't know if you remember that, where everybody was using like 40, 50% Class F and Class C fly ash, thinking they were creating a more durable concrete. Well, as it turns out, what we were thinking is we're diluting the cement and pulling out the alkalis. And the scary thing is, a lot of these ashes, a lot of these supplementary cementitious materials, they had alkalis all their own. And at the percentages that we were bringing, we were kicking ourselves in the ass or shooting ourselves in the foot. So that was the second thing. We had these higher alkali cements, finer cements, and then we're going to these lower quality supplementary cementitious materials that either have cleaning agents on them, they've got higher carbon contents, more impurities, or we just don't have them anymore. Lower pozzolanic materials or lower silica contents. Mm-hmm. The ashes that we were using years ago, decades ago, are a far cry from what we are using today. I think we can both agree on that, and a lot of your listeners will agree on that too. The last thing is the inevitable reality, and I don't care if you're a Scientologist, if you're Christian, Catholic, Jewish, it doesn't matter if you believe the earth is 3 million, 3 billion, 3,000, or we're from aliens. We only have so much rock that we can get to on this big blue planet, right? This big blue marble. We happen to have had some of the best geological engineers, or PGs, throughout time, helping us build this infrastructure and the structures that we use for our civilizations. You look here in New Jersey, I'm writing a book now called The Concrete on My Block. You know, the first chapter is aging the concrete based on the type of rock in there. Because here in Freehold, New Jersey, we don't sell river rock anymore for concrete. It's all crushed rock. But when I run through the subdivision that my parents live in, you can still see copious amounts of river rock in the concrete that was made in the 20s and 30s. So the reality is the concrete that was the best to use, or the aggregate to use that was the best for concrete, the least reactive, we've use that crap up. And now what we're getting into, especially our sands, is you get what you get and you don't get upset. That's why these technologies like E5 nanosilica are so gosh darn important, because this is the perfect storm. We've got different cements coming in. Our SCMs are, if you're in New Mexico and Texas, they're Dunzo and Gonzo. California, New Jersey, they're rounding the corner of never coming back. And ASR is a real thing that's becoming more of an issue faster.
Yeah. Yeah, I think that's what I was getting at, was trying to say was the ASR is based on what's available to us now. So we need a solution to prevent it. So what I saw in the spec was to offset the amount of cement with an SCM to prevent ASR. And what I had was a ready mix producer, reach out to me and say, hey, based on the availability of the SCMs in our area, we're concerned that we're not going to be able to meet this ASR spec.
Yeah.
If we're not capable of obtaining an SCM to help that, is colloidal silica a solution that we can use?
So we're working in the Western U.S. business unit with a concrete provider that's having that problem, where if the DOT would allow him to go to 32% FASH, he might be able to get below the 0.1% expansion at 14 days. Might. They won't let him go above 25%. So what we've done is we've used, do you allow me to say product names on this for your listeners?
Yeah. No, I think people can do their own homework. If you hear a product on here, do your own homework.
And that's the thing. Like, what works for them in the Western U.S. business unit, you got to do something different on the East. And that's every freaking concrete additive.
Concrete's a local product. You got to do your own testing on what you can get your hands on.
And that's one of the things I want to comment on. But what we're doing is this stuff is so reactive with ASR, it glows in the dark. That's not true. It doesn't glow in the dark. But without ash, just straight cement, they're at 0.8% expansion at 14 days.
Okay, can you explain if that's good or bad?
ASTMC 1260 and ASTMC 1567, one of the most disputed sets of tests in the concrete industry. It's the accelerated mortar bar test. It's a 14 and 28-day test. It's a 1 inch by 1 inch by 11 inch beam, set of 3 beams that are cast with these metal nuggets at the end of them. And what you're ultimately doing is measuring that bar over the length of 14 or 28 days, right? This bar is a bastardized version of your mix. It's not a real concrete mix. It's a mortar mix, right? It's a 440 grams of cement, 990 grams of your granular skeleton based on a grinding and sieving process, and a 0.47 water cement ratio. Now you let that cure for 24 hours, you put it in a tap water bath at 175 degrees Fahrenheit. After that 28 days, you take a measurement, then after that 24 hours, take another measurement. It goes into a sodium hydroxide bath for 175 or at 175 degrees for 14 days. And over that 14 or 28 days, you measure that change in length. Now, remember, I said it's in a sodium hydroxide bath at I believe it's a 0.4, it's either 0.4 normal or 0.4 molar, I can't remember, solution. This is the optimal environment for the alkali silica gel to grow. Now, this is not a real world environment. It's not realistic, because this is called the accelerated mortar bar test, right? So this is pass fail, right? If in that 14 days, you're under 0.1% expansion or growth, then you're good to go, right? If you're working with an airport, that same time frame, or excuse me, that same test is now 28 days, and I think they're using 0.08% expansion. But ultimately, it's an accelerated mortar bar test.
Okay.
Now, what you're doing here is you've exposed aggregate surface area, you've created a very porous matrix, and you've given the alkalis or the mortar the alkalis and the temperatures for that ASR to thrive and survive quickly. So when somebody says 0.8% expansion, that's 8 times the legal limit.
So is that test trying to replicate a period of time? Is that what that is?
No, it's just really trying to give you a pass-fail. Ultimately, what you're supposed to do is, and rarely folks do this, and I'm going to get a lot of heat for this, is they're supposed to marry that test up to an 18-month test, where you're putting the alkalis into the concrete and you're keeping it at a lower temperature at 75 degrees Fahrenheit, but you're 18 months instead of 14 days. And who the hell wants to do that test?
Yeah.
Now there's a 56-day test that's coming out, and there's a longer version of that universities run on Treat Island, where they're doing like a 3-4 year test. Huh. So there's different ways of testing. But yeah, the 0.8% expansion that's very reactive. So when we were using 20% Class F ash with this ready mix provider, it was still at 0.3% expansion. So they kept driving it up, and at 32%, they were at 0.11, which, with standard deviation, that drops it below 0.1 just by a hair. So what we're going after now, or what we went after, is using the maximum they're allowed, 25% Class F fly ash, with a combination of nanosilicas from specification products. The E5 Plus and the liquid fly ash. Now, like I said, the dosages, it will vary based on how much you have to use, how reactive your aggregates are, so on and so forth. So we're using 8 ounces per hundredweight of the E5 Plus, and then we're using 24 ounces per hundredweight for LFA. And that is getting us well below the 0.1% expansion.
100 weight of cement? Is that what?
Yes, sir. So you're using this as it was an admixture.
Yep. And
the nastier your aggregate, the more of this admixture you have to use, because you're getting those nanosilica particles. So
what are you just doing tests and showing that you can meet it by using this colloidal silica with the fly ash? So you're doing the same test. Okay.
The accelerated mortar bar test that the Department of Transportation accepts, that's the test that we're running with that combination of Class F fly ash and that E5 nanosilica.
And it's a 14-day test?
Yes, sir.
Okay. All right. Yeah, I'm just thinking when we run across this, how long it takes to, because usually we bid on a job and you get a set of specs, and then you're pricing based on the specs, especially a government job. You can't sway off the specs at the beginning. So if you get the job and say, hey, depending on what supplier we use, we could possibly use the colloidal silica based on the products that they can get their hands on, because not every producer uses the same materials.
I want to push back on that a little bit, and I guess this is a question, or really a statement and a question for you. I've been on plenty of government projects, whether that's building a taxiway for an active runway, or it's normally pavements, and then there's pilasters, and then there's parking aprons. When the proverbial SHIT hits the fan and they're not getting ash anymore, the engineer of record that we worked with on plenty of these job sites wanted a solution.
Mm-hmm.
They would not move forward if there wasn't something in there taking care of a known issue, not just with the ASR, but a lot of these other issues like calcium oxychloride formation. It relies on the same mechanisms that the ASR gel relies on. Chlorides, hydroxides, alkalis, permeability, and moisture. So if you can solve an ASR problem, more than likely you're going to solve other problems. And to piggyback on that, can I just show a project that we ran on an airport?
Yeah.
So this was something that was, the first commercial application of nano-engineered concrete in the U.S. This is something that we did as part of my PhD work with the Army Corps, with Lafarge North America, with Eagle County Airport. It was an awesome job. And one of the ready mix providers that I worked with back when I was in the industry was having a problem that the concrete that they were using, not only was it not setting up, they were having time of set issues, but what they had to do to get it to set up in time was causing durability issues, and they were ripping and replacing concrete a lot sooner than they had intended. And this is published in Concrete International if you want to go there and see the results. So ultimately, they were trying to get 3,500 PSI in 24 hours. This taxiway was in front of an air rescue facility, so they had to be able to take off in 24 hours with their almost look like MRAPs, just these huge freaking vehicles, these firefighting vehicles. So a lot of powder, low water cementitious ratio. The reference mix is on the left. The nanosilica engineered concrete is on the right. And ultimately, we had to use at least 20% Class F fly ash. So for the nanosilica mix, we took it from 20% to 19.5 because that's 20% Class F fly ash, and the engineer felt comfortable. And then we used 0.5% nanosilica. We ultimately could reduce our high range water reducer, and that's something that we find with nanosilicas, that they increase the efficiency of everything around it. We not only did hand placement of this pavement, but we also did a slip form paver. And again, we were trying to achieve 3,500 PSI in 24 hours, 5,500 at 28 days. So slump was one of their biggest problems. Every time they got to the job site, it was only a 15-minute drive, but because it was on a runway, we had to do a lot of security sweeps. So it took them about 45 minutes to get through security. So ultimately, it was at 60 minutes when the slump just started dying off. So they ended up having to they ended up having to increase water to get it to the point where they could do hand placement. With using the nanosilica, we were able to increase our slump evolution or slump life, so they didn't have to include water. With that, and with the use of nanosilica, we saw a significant increase in our cementitious efficiency through strength development. Before they were using this, they were increasing their cementitious content by more than a sack and a half, and they were using 2% non-chloride accelerators to get the strength in 24 hours. And again, please bear in mind, this is Colorado in the winter, so very unforgiving. The mortar bar at 14 days using the nanosilica in addition to the mix, just like we did, replacing the Class F flash, I apologize. We were able to meet and come well below the requirement for the accelerated mortar bar expansion. As you can see, what they were using, even though they were using 20% Class F fly ash was changing. It was in 2014. We didn't really know how drastic it was, or the industry didn't understand it at this point. But we had to wait to release this data until they can start increasing their ash content and start meeting the grades. But ultimately, what we did is we came back 7 years later, and what we did is part of the PhD was comparing conventional concrete to this nanosilica enhanced concrete. So 7 years, we came back to look at concrete that was placed the same day in the same wheel path by the same contractors and how it was impacted by the abrasive environment with the non-chloride accelerator, or with the chloride-based de-icing salts. We use mag chloride, as well as the heavy traffic. And you can see the moderate to extreme surface where we got exposed aggregate and they didn't have to pay for it. With the standard concrete and using the nanosilica, little to no surface abrasive wear. And then when we zoomed in on it, you can see where the aggregate is showing through, and then you can still see the burlap lines that you get that are being drugged behind the paver. And again, these were both placed on the same day.
Wow. Yeah,
Yeah.
that's cool. I'll have to actually post this on our YouTube channel so people can see this. It's good stuff.
Oh, heck yeah, man. Heck yeah.
Yeah. So it sounds like out of that example, what I heard was on top of the ASR concern, you were able to address, it looks like you reduced the amount of high range water reducer as well.
We did, but if you looked at the mix, that was already a rich man's golf course.
Okay.
They were using 12 fluid ounces per hundredweight. The water cementitious was 0.35. This is when we were still starving mixes. And this came off the heels of this Chronolia road patch that I had designed. So 12 fluid ounces per hundredweight. They didn't need that much to begin with. It was because it was setting off like a bat out of hell that they were putting that much in there, and then adding a little bit of water and it was blowing it back up. So they didn't have to use that much, but.
Okay. So maybe that wasn't a benefit of it, but
you will get that. There's some wonderful research by Konstantin Sobolev at a University of Wisconsin, and he's the guy who introduced that concept that nanosilica does increase cement efficiency, or the efficiency of polycarboxylate style high range water reducers. So that is a fact.
Because to my understanding, it basically fills in the voids in concrete, or makes it more pumpable. Is that a good way to explain it to us laymen?
Can I show?
We're not Dr. John.
No. Can I have a picture that gets into it. Do you mind if I show that picture?
Yeah, show the picture, and I'll try to explain it. Because you made that before you get in there. You were trying to explain to it. I thought it was on here. Maybe it was a previous conversation, but it's like ball bearings together.
Yeah. So there's a few things that we get from nanosilica, but then it's also a nanoparticle. So what you were talking about is something called particle to particle packing. Right? That's a void filling thing where there are these really small spaces in between hydrated components of concrete that there's water in, and we can't get ball bearings into if that's what we're going to steel ball bearings.
Yeah.
Nanosilica itself, or any nanoparticle, if it's really hard and it's some reason it didn't react, if it gets in those spaces, it's going to pack those spaces and absorb the catastrophic forces that would cause ultimate failure. So that's what you were talking about. But when we're targeting nanosilica specifically, and I really want to be specific to nanosilica if that's okay, there are three things that we care about. And there are, I tell you asked me for some papers yesterday. I have an entire folder called Awesome Nanosilica Papers, and I didn't want to scare you and send all 200 papers. And that's the thing for the audience. When you start looking at new technologies, Seth said all of us have to do our homework. The great thing about nanosilica is that there are so many flipping papers. Even if you wanted to ignore everything that Jon Belkowitz did, which, hey, I ignore a lot of what Jon Belkowitz did, and proof in the pudding, so I can learn something new. And I'm reading a paper on nanosilica every single freaking day. I have a bunch of them on the floor right here. So there is a copious amount of information out there that really gets past the question of, has this been done before? Has it been done on different ashes, different cements, yeah, everything that you could possibly ask, it's been done with nanosilica. So there's three things that we care about. One is, since it is a silica, since it's amorphous, it will react in the classical way that we know is called the pozzolanic reaction. But because it's so small, and because the force field over it that keeps it in suspension is small, right? That pozzolanic reaction happens instantaneously. There's a wonderful paper that was written back in 2012 by Land and Stephen that talks about this instantaneous pozzolanic reaction that they refer to a calcium silicate hydrate seeding effect because it happens so fast. That normally wouldn't happen with silica fume, class F fly ash, or anything else that's in the micro realm. Now, the other thing that we get from this nanosilica, because reactions start happening so fast, the cement, the parent material, wants to dissolve more. It wants to liberate more calcium in the solution to give us calcium hydroxide for this pozzolanic reaction, this instantaneous pozzolanic reaction, and this calcium silicate hydrate seeding effect. Faster and a higher rate of cement dissolution compared to grinding up the cement finer. And BTW, when we grind the cement up finer, we have a tendency of keeping the same cement efficiency, that we create a hard candy shell, an M&M hard candy shell, where not only do we grow our phases around the cement particle and into solution, but we grow a diffusion barrier, that M&M hard candy shell, into the cement particle, even if we grind it up fine. By using nanosilica with all these reactions happening faster, our tricalcium, our dicalcium silicate, our A-light, our B-light, our freaking soccer ball of cement dissolves so much faster. There's a wonderful paper written by Bjornstrom et al. From 2003, 2004 that goes into this in detail ad nauseum. The last thing that we get from this, it's a really fancy schmancy term. It's called heterogeneous nucleation, which means even if we have spent up all the pozzolanic reactions, we have no calcium hydroxide in the localized area of the silica to convert over to calcium silicate hydrate, even if we have exhausted the pozzolanic engine, because the nanosilica is nano, and because it has this really small force field on it, like I drew a picture of it, it will have something. See here on the left, it shows a micron-sized particle. In solution, it has this really big force field. A nanoparticle, it just can't have that size force field on it because it's so much smaller. It has a higher specific surface area. Because of that smaller specific surface area, because of that smaller force field, it will have something called heterogeneous nucleation, which is a really fancy schmancy way of saying, because something is small, other things will want to grow on the surface. So that calcium silicate hydrate, it will interact with this nanosilica and it will want to grow on the surface, and then we'll have more germination of this thing that I keep referring to, this calcium silicate hydrate, which is the backbone of concrete strength. I love nanosilica, man. Damn, that's good stuff.
So it increases the strength.
It increases the production of calcium silicate hydrate by monopolizing water, calcium hydroxide, and in doing so, strength is increased, and what we already talked about, durability is increased. But we're increasing strength by increasing the cement efficiency. So what they've done in Indiana is they've been able, and this is what Joe talked about, they've been able to reduce their cementitious content by bags.
Yeah.
Not by 3%, by a ridiculous percent.
Yeah, because you like you said, it's making the cement that you're using more efficient, so
Totally.
you're able to use less. How's it? I guess it wouldn't matter if we're using type 1L then, because type 1L is basically you're cutting cement out of there, adding limestone to it. So does the nanosilica kind of it doesn't care about the limestone? And
Oh, it does. It does. It does. This is why I go back to product names because, hey, man, there are a bunch of folks out there that produce nanosilica in suspension, and there are a bunch of folks out there who produce something in a bottle that they claim is nanosilica. And that was one of the things that I wanted to make sure we attacked in the specification, that the BS products out there that weren't nanosilica, we had a way of shedding light on what was real versus what is fake. But not all nanosilica is created equal. The reason why I work with Spec Pro is that they have made this process of using nanosilica a lot more palatable for the industry, a lot easier to start using it, and a lot more cost effective too. Did that answer your question? I feel like that answered your question.
yeah, no, I think I think you answered it. So we're using it on the cements that we have today, and again, we got to emphasize that just because Jon used it in Colorado and had great results, we still need to do our own testing in our local area with our local producers.
Wait a second. Jon didn't just use it in one plant at one job
No.
site. This
The
has been
example that
15
we went
years.
through, I will clarify. We went through an example of your first time using it, in Colorado. So just to clarify. So anyhow, there's got to, and you're working on a standard. So we all can compare whatever colloidal silica product that we are electing to use. We can put it against the standard and make sure it's meeting standard. That's one of the things that folks are working on to make sure that we're getting quality colloidal silica products. What I guess with anything that we discover that it seems to be fantastic and we want to use it, is there a threshold the amount that you can use,
Oh,
and then it becomes detrimental to the concrete?
especially when you're using nanosilicas that really are just folks taking it off the shelf. Part of my PhD, and God bless the U.S. Army Corps for paying the majority of it, it was to understand not only how nanosilica can help concrete with ASR durability, but what was the back end of the curve? When did it start going bad? And when you look at, I think it's either chapter 3 or chapter 4, that was an entire year and a half dedicated to figuring out what could go wrong. And yeah, man, just fly ash, just like polys, if you use too much of it, bad things start to happen. There's a point though where you're like, okay, I'm spending too much money. This is too expensive. And that's normally what you reach. But shoot, there are DOTs that have used nanosilica blindly. And I'm not trying to be a jerk and calling anybody out, but man, I really want to. That against the better consultation with us and the judgment and the advice that we gave them, they use the nanosilica like silica fume. And holy moly, they're putting 10, 20 gallons per cubic yard to get 6% solids. Like, I don't even know how they got that in the mixer. And of course, their results were horrible.
Right.
So the reason why you work with professionals like the folks at Spec Pro who have put in the investment on identifying the best type of nanosilica, how to use it, all that shtick, is you get past all the BS. It's the same reason why I worked with Crezo with my high-range water reducers back in the early 2000s. Lou Cook knew what the hell he was doing when it came to marrying up the right polycarboxylate to the cement chemistry and the sequencing. It was a lot more palatable and easier to get W's working with that than all the other high-range water reducer providers who would say, hey, this one works with any cement in the world. You just have to change up the dosage, which was BS.
Right.
I did want to show you something else besides that one job site that we did in Colorado. We also did other work with.
You only used it that first time.
One time. So this is from some of the work that we did with the U.S. Army Corps. And like I said, there are so many freaking different ways of testing ASR gel. One of the hardest things to do with ASR gel is look at the gel in an undisturbed state. Anytime that we look at the gel using petrographic analysis, it's normally from an accelerated mortar bar. We cut the bar in half, we put it in epoxy, we polish it, blah, 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 and then we put it under the microscope. But effectively, we are destroying the gel, right, before we look at it. This is a test that we ran with the U.S. Army Corps, and it was using a British test that I just flippin' love. It's called the BS7943, the ASR gel pat test. And what you're doing is you're creating this little pervious puck of mortar that allows water and salts to go through it. And you're doing that with your reactive aggregate and just enough paste to cover the surface.
Okay.
You're putting that puck in a cement pore solution bath at 125 degrees Fahrenheit for 72 hours. And then you do an area fraction analysis of the amount of gel. And if you look at these pictures, the white fuzzy stuff is the ASR gel. And you do that under 2 microscopes. So what I love about this test is it allowed us to see, you remember before I showed you that ASR gel rosette under a microscope, it allowed us to see what the nanosilica was doing to the ASR gel morphology or the structure of the ASR gel. And before I told you, it was the needles that create these really tiny pores that draw in the water and salts, and you can see these on the left here. The ASR gel with using the nanosilica, we've changed that up. We've changed up not only the structure of that fibril or that wispy-like, needle-like morphology, but we've also changed up the pore space. So we increased the diameter of those needle-like fibrils, as they're called, of the ASR gel. And in doing so, we increased the space between those needles. And what we also do is change up the viscoelastic properties, the elasticity of the gel too. So again, it's not just a chemical approach, but this mechanical approach is it's not going to imbibe as much water. When it does try to expand, it's not going to be able to expand. And if I have it in here, I don't have it in here. I'm so sorry. What we also did is a chemical analysis of the gel, and we found out that the gel on the right had less soluble alkalis in it and more silica, and the gel on the left, that nasty gel, had less silica in it and more of those soluble alkalis.
The bad stuff.
The bad stuff.
Yeah. Huh. Well, cool.
I find this stuff absolutely amazing because understanding the why behind the nanosilica having a positive impact on durability is extremely important. Based off of what we understood and how the nanosilica interaction with the hydrated cement matrix monopolizes and dominates salts, led us to our work with Jason Weiss at Oregon State University on how the nanosilica has a positive impact on calcium oxychloride formation reduction. And Jason's own words, it's nanosilica is more effective than any other SCM out there in reducing that calcium oxychloride formation. You got to check out that flipping paper.
Yeah, I got to. Dr. Jason Weiss is on my list.
And it goes back to, and he's another person you got to have on your podcast. Jason Eidecker, Jason Weiss are two. I would say Jason Eidecker is one of the most brilliant minds in alkali silica reactivity alive today. There's also Maria Younger, Kevin Folliard, of course, Kimberly Curtis from Georgia Tech. And then the list goes on, but I would definitely say Jason Eidecker is number one that you should probably talk to about the future of ASR in concrete. He's also the guy that writes a lot of these standards up, and he flippin' hates the accelerated mortar bar test. And then Jason Weiss created the test for calcium oxychloride formation. I mean, he literally created the freaking test that we use today. So, yeah, both of them are flipping awesome.
Great. I think, dude, we covered a lot today.
We haven't covered everything, though.
We haven't, and I think we need to maybe pause for today, and then we'll have to circle back again. And I think we just barely cracked open your book of colloidal silica, because I don't even think we touched the 15 questions I had on here, but it was all good information. So I guess to surmise is this is a product. This is another SCM solution that could help us reduce the amount of cement that we're using, and also has some other benefits to the concrete as far as durability. Is that a good summary of what we covered today? Don't go any further, because we're gonna come back.
I would just flip it. I would flip it. I wouldn't put cement reduction as the number one.
Okay.
I think this solves our SCM issue. Whether or not it's I have a crappy SCM that I need to get a little more bang out of, or, dude, I don't have any SCMs.
Yeah.
So I think that's the number one thing that it solves. That all the other stuff you said is absolutely right. But right now, when it comes to ready mix providers and what's on their mind, there's also carbon footprint, blah, blah, blah.
Yeah.
I think durability in SCMs is huge, man. Huge.
Yeah. Yeah, that is huge. And now I understand why Joe calls his product Liquid Flash. It makes more sense to me after our discussion today. So thank you for that, Jon. I will always point everyone to Intelligent Concrete, and your coffee talk is 10:30 on Thursdays on LinkedIn. Is that right?
We have 3 of them. So one is on Wednesday, then the other is Thursday. Wednesday, it's Eddie Stone. Thursday, it's Intelligent. And Friday, it's Colloidal Silica and Concrete Association.
Oh, okay, cool. I have to check Fridays out. And then you want folks to visit you on YouTube. Of course, you got hundreds of videos on YouTube. Good stuff there. Anything else you want to share with us today before we leave?
I've learned that in our industry, there's only 2 ways of getting people to participate, and that's buying them beer and pizza or getting them pissed off. So for your listeners out there, this is a call to action. If anything in this pissed you off, I am excited and looking forward to working with you. On the opposite end, if you got really excited, I'm also excited to try this out with you. This is a new technology. You should be a naysayer, because that's how we progress in our industry. So call to action. Let's get to work, y'all.
Yeah. Thank you, Jon. I appreciate your time today, and we'll definitely do it again.
Awesome sauce.
And that concludes another episode of the Concrete Logic Podcast. I hope you got some value out of that episode and learned a thing or two. If you did, visit our website, concretelogicpodcast.com, click on the show support tab, and learn how you could be listed as a producer of an episode. Again, that's concretelogicpodcast.com. Click on show support tab to learn how you can support the show. And as always, Mike Dunton will take us out.
That alarm always sings couple hours before the sun comes up. Open up the side, put some diesel in the lights, and wait till the trucks roll up. Yeah, this ain't how most folks live their lives, dripping in sweat, working overtime. But while they're tying their ties for their 9 to 5s, we're out here changing these skylines with wood, iron, and mud. We work hard for a dollar, give thanks to the Lord above. Never make a man do something you can't prove. Hard work calls for a drink or two. Expect more, it's real.